Okay, so it's 6:02. Let's start. So welcome everyone to our ITMP seminar, and today we are happy to have Xinan Zhou, and he will speak about holographic correlators and emergent Parisi-Sourlas supersymmetry. Please start.
Okay, thank you very much for the invitation to give this talk. So yes, today I'm going to talk about holographic correlators, and my talk today is based on these two papers from last year with Fernando Aldai and this more recent paper from January with Conor Behan and Pietro Ferrero. And please stop me at any point during the talk if you have any question. So let's start with some very basic ADS-CFT. We all know that ADS-CFT maps string theory or M theory on ADS times sphere to a superconformal field theory that lives on the boundary of this space. And it gives a dictionary that matches the observables on both sides. In particular, the most basic observables in the CFT are the correlation functions of local operators, and they become the scattering amplitudes in the bulk space, the ADS space. We can study this correspondence in various different limits, and the most tractable limit is when the bulk theory becomes a weakly coupled supergravity theory. So this happens when the central charge of the theory is large, and if it's a string theory, further need to tune the string length to 0. So today we are going to look at these holographic correlators. And let me first give you a few motivations for why we are interested in that. So the first motivation is that we can use these holographic correlators which essentially can be computed using perturbation theory, and we can use that to learn about strongly coupled physics. So we all know that quantities which are not protected by supersymmetry are very difficult to compute using field theory methods at strong coupling. However, using ADS-CFT, this is becomes the perturbative calculation, which is more manageable. And also for some theories which don't have a Lagrangian description, such as the 2,0 theory in 60, then using ADS-CFT is the only method to make progress. The second motivation is that we can also go in the opposite direction. So actually, in the bulk, if you want to go beyond tree level and do loop level calculations, this is technically very difficult if we want to do it directly. But on the other hand, this is also not necessary because the fact that we have a CFT on the boundary allows us to use many of these powerful bootstrap techniques. And these techniques allows us to compute loop corrections by just inputting the tree level data. So there is a systematic method which can be viewed as an ADS version of the unitarity method in flat space. And it is illustrated by this cartoon here. So essentially, we can just take these tree level diagrams, amplitudes, and we can glue them together to get a one loop correction. So studying these holographic correlators gives us a concrete setup where we can study the quantum effects of ADS gravity. And this also goes beyond just the two derivative supergravity. You can also incorporate higher derivative corrections coming from string theory or M theory corrections. This can be done by combining this ADS unitarity method with other techniques such as supersymmetric localization. And studying these holographic correlators provides precision tests for the ADS-CFT correspondence. Now, the final motivation has to do with the connection with flat space scattering amplitudes. So everybody knows that in flat space, the scattering amplitude program is highly successful. There are many efficient methods to compute amplitudes without ever using diagrams, and these amplitudes, they reveal very rich mathematical structures. So we may want to interpret this progress as new ways to think about QFTs. as in like we don't even need a Lagrangian. And if that's the interpretation, then these lessons we learn from flat space, they should also have generalizations into curved space-time. And there is no simpler curved space-time than the ADS space, and it is the perfect playground for us to start exploring these extensions. Another point about scattering amplitude in flat space is that from them we can learn a lot about the symmetries of the theory, which are otherwise not manifested in the Lagrangian formulation. So you can ask also the same question here. So by studying these holographic correlators, what kind of symmetry properties can we learn about these ADS theories? So that was the motivation. Now let's start to become a bit more concrete. So first, let's ask what kind of theories we are looking at. So I'm only going to focus on the theories which have the maximal amount of supersymmetry to have the most analytic power. So these are the theories with 16 Poincare supercharges. And in d greater than 2, there are 3 possibilities. So these are the 2B supergravity on ADS 5 times 5, and that is due to n equals 4 supermills in 4 dimensions. And we can also have 11-dimensional supergravity either on ADS 4 times 7 or ADS 7 times 4. And they are due to the 3D. Now the second question is what kind of operators or particles we are looking at. So in all these theories, we start with a higher dimensional theory, and then we perform Kaluza-Klein reduction on the internal sphere. And that gives us infinitely many KK modes. Now these modes, they are organized by superconformal symmetry into supermultiplets. And the operators or particles we are looking at are the superprimaries of these multiplets. The more precise dictionary is given as follows. So on the CFT side, we are looking at these operators, which are called 1/2 BPS because they preserve half of the supersymmetry. They are labeled by some integer k, and in the bulk, they correspond to some scalar field. Now, these operators, they carry k vector indices and transforms in the rank k symmetric trace interpretation of the asymmetry group SOQ+1. In the bulk, this SOQ+1 is nothing but the isometry group of the internal sphere. And this integer k is just the amount of angular momentum we have on the sphere. Now, these operators, because they're protected, their conformal dimensions are quantized. So their conformal dimension k, delta is just proportional to this kk level k with a proportional constant epsilon, which depends on the spacing dimension. And in the bulk, this just corresponds to a protected squared mass. So there are infinitely many of these multiplets. The most familiar example is the k equals to 2 case, which is the stress tensor multiplet. And for these operators, the 2-point and 3-point functions are trivial because they're essentially just determined by symmetries. And the first non-trivial case is when we have 4 operators, and that's the thing we are going to focus on today. And I'm going to look at 4-point functions with different k1, k2, k3, k4, and there are infinitely many of them. So are there any questions at this point? Okay. Now, before I proceed, let me first briefly remind you how these holographic correlators were traditionally calculated. So the old method is basically a brute force diagrammatic expansion in ADS space. And the way we do it is very similar to what we do in flat space. So the first step is to find the Feynman rules in ADS. And so here we are looking at 4-point functions at tree level. So the thing we need are the propagators and also vertices, both cubic and quartic. And finally, we need to know how to do the integral over ADS for the vertex insertions. Now, once we have these rules, and for a particular 4-point function, we need to enumerate all the diagrams that can appear in this correlator, and we need to evaluate the diagrams one by one. And finally, we add up all the diagrams to get the correlator. Now, this may sound like a very straightforward procedure, but in practice, it's a very painful thing to do. One reason is that the vertices we needed are extremely complicated. The case of ADS 5 was completely worked out by Rutunov and Frolov, and but you can see the final answer for the complete quartic vertices is extremely complicated. Also, when we start to look at more and more general correlators, there are more and more diagrams appearing in the calculation. So this is a very difficult thing to do in practice. So because of these difficulties, the traditional method only produced a handful results in the older literature. I should mention here that this method was further streamlined in 2018 by Rutunov and collaborators, and more examples were computed. But in the older literature, there were only very limited results. Most of them are in ADS 5 times S5. There was one example for ADS 7 times S4, and there was nothing for ADS 4 times S7 because the exchange diagrams couldn't even be evaluated in a closed form. And in all these cases, the answers you get are they have a huge size, and the complexity of the answer grows quickly with the external dimensions. So from these results, it's not at all clear what the general structure is, and it's impossible to get from them the organizing principles for these holographic correlators. On the other hand, in recent years, there has been quite a lot of progress using Bootstrap ideas. And one lesson from these Bootstrap developments is that we now know that these holographic correlators, they actually have very rigid structures. So essentially, they can just be fixed by symmetries and consistency conditions. So in a few slides, I'm going to very briefly review these Bootstrap approaches and the results we can get using these methods, but that's not the main point of today's talk. Actually, the purpose of reviewing these results is to show you the intrinsic limitations of this Bootstrap method. And then I'm going to introduce a new method which will overcome these shortcomings. And now let me also take this opportunity to set up the stage by introducing some superconformal kinematics. So, so we are looking at these 1/2 BPS operators. As I told you earlier, they transform in the symmetric truth distribution, so they have these asymmetry indices. One nice trick to keep track of these indices is to just multiply them with some null vectors. So by null, I mean the inner product of these vectors t is 0. So this condition guarantees that whatever is multiplying this string of vectors is automatically projected to the symmetric truth distribution. Now, doing this by multiplying these null vectors, the 4-point function has become a function not only of the space-time coordinate x, but also of some internal coordinates t. The second step is to use the conformal invariance and also asymmetry invariance to extract a kinematic factor. And then the 4-point function can now be written as a function of the invariant cross ratios. So here, U and V are the standard conformal cross ratios, and we have also defined sigma and tau, which are the symmetry analogs of these cross ratios. There is a number, this curly E here, called extremality. It is determined by the external weights. And roughly, it tells us how complicated this correlator is. So the reason is that we can see from this definition that this function, function of cross ratios, curly G, is a polynomial of the asymmetry cross ratios. And the degree of this polynomial is this curly E. Now, so writing the correlator like this actually has only used the bosonic part of the superconformal group. There are also fermionic generators, and they impose further constraints on the form of the 4-point function in the form of superconformal word identities. Now, to write down these superconformal word identities, let's introduce a change of variables. So first we write U and V as Z and Z bar. And similarly, we write sigma and tau as alpha and alpha bar. Now the superconformal word identity simply tells us how ZZ bar and alpha alpha bar are related by this differential constraint along this slice. And let me remind you again, this epsilon here is associated with the space dimension. Another ingredient I need to introduce is the so-called mating representation. And this representation has the advantage that the analytic structure becomes much clearer. So the idea is very simple. We take this 4-point function of cross ratios and we perform two mating transformations with respect to U and V. The dual variables are S and T, and we can think of them as the Mandelson variables in flat space. We also introduced the third Mandelson variable U, so that things are more symmetric, and they satisfy the constraint that S plus T plus U equals to the sum of external dimensions. So this is very much the same as in flat space, where the right-hand side is the sum of squared masses. It's also conventional to take out a product of gamma functions. These gamma functions are there to capture the double trace operators in the 4-point function. And these double trace operators are always there for holographic CFDs because at large N, we always have these double trace guys. Now, all the information is now transferred from this curly G to this curly M, which is called the mating amplitude. And that's the thing we are going to focus on in today's talk. Great. Now we can immediately see this is a very good representation by just looking at individual Witten diagrams. So if we look at the first contact diagram, where we have 2L constructed derivatives at the quadratic vertex, then we find the mating amplitude is just a degree L polynomial, and this is the same as in flat space. For an exchange diagram, the structure is similar but slightly different. So instead of having just one simple pole for the Mandelson variable, we now find there are infinitely many poles. The poles, they start from the so-called conformal twist, which is defined as dimension minus spin. And there are also some infinite many satellite poles, which correspond to the conformal descendants associated with this primary operator. At each pole, the residual is a polynomial, and also there's some regular piece. There are two comments I will make regarding the exchange amplitude. The first is that this regular term is actually sort of ambiguous because we can actually choose different cubic couplings which are equivalent on shell, but changes the 4-point changes the diagram by some contact interaction. And another point is that for genetic spectrum, there are infinitely many poles, but for some special theory with special spectrum, actually we find that the poles, they truncate to only finitely many. So this happens for ADS 5 times S5 and also ADS 7 times S4, but it does not happen for ADS 4 times S7. And this truncation, actually, one can see that from basically just as a consistency condition of the 1 over any expansion. Great. So these are all the ingredients I need to review these bootstrap methods. So there are 3 of them. So let's first start with the first one, which we call the position space method. And that is really just a proof of principle to show the idea works. So it's very much similar to what we do using in the traditional approach. Sorry, with that question?
Yeah, can I ask you something on the previous slide?
Yes.
So you have this product of gamma functions. And can you comment what happens with it, like in 1 over n expansion at non-perturbative level? Because if I understand correctly, like at finite n, you cannot like define consistently double trace operators or something like that.
Right.
So do you have any idea what happens with these gamma functions?
I don't have much to say about that. There's the paper maybe from 2 years ago by Zhou and Sasha on this unperturbative mailing. Yes. So right. So the question also is also related to that. In series, you have these accumulation points on a twist. So even if it's not any large n theory, you always have this accumulation to the double twist operators, for example.
Okay.
So, yeah, thank you. Right. So about this first method. So the idea is as follows: we first write down an ansatz as a linear combination of all the diagrams that can appear, both exchange and contact. But we don't fix the coefficients. So these coefficients would be fixed if we knew the precise vertices, but we also know that that's the most difficult part because the vertices, they can take many pages. So instead, we are going to leave them as some unfixed parameters, and then we fix these parameters by imposing the word identity for superconformal symmetry. And turns out that this indeed works, and all the parameters are uniquely fixed. So that tells us symmetry is indeed powerful enough. But of course, this method is not very efficient method because first we need to compute many diagrams still. And also it becomes really cumbersome when we go to correlators with higher weights. Now there's a better version of this idea, which is the second method. So in this second method, we reformulated this task of computing correlators as solving some algebraic problem in mailing space. So it goes as follows. So we first take the superconformal word identities in a potential space and we solve it. And we find the correlator takes the following form. It has a protected part and also a dynamical part. So this dynamical part is denoted by H, is sometimes called the reduced correlator, and it is acted on by some differential operator D, and this D is completely determined by symmetry. Now we want to use this in mailing space, so we just do many transformations on both sides. One can argue that this protected part G0 actually does not contribute to the mailing amplitude, so we can just ignore it. And on the left-hand side, we have already defined the mailing amplitude. On the right-hand side, we similarly define a reduced mailing amplitude M tilde from this reduced correlator H. And this differential operator D is going to become the difference operator in mailing space. And that gives us the relation between the reduced mailing amplitude M tilde and the full mailing amplitude M. So this relation takes care of the superconformal symmetry, but there are also other conditions to impose. So we also have conditions about the analytic structure of the full amplitude M because we know where the poles are, and we also know the residuals should be only polynomials. Also, there's pole symmetry, and also we know the asymptotic behavior of M because it should go to the flat-based amplitude. And when we impose all these conditions together, we get a very constraining algebraic bootstrap problem. And the only thing we need to do now is just to solve it. And this was problem was set up for ADS5 tensors phi and completely solved, and we got all the 4-point functions. So the advantage of this method, the first one clearly is that we don't need to compute any diagrams anymore, and we can solve all the correlators in one go. And this same method can also be set up for the ADS7 tensors 4 case, but it also has some limitations. So first of all, by going from M to this reduced amplitude M tilde, we lose some insight about the analytic structures. So a priori, we don't know what this M tilde should look like. And for this reason, the ADS7 tensors 4 case, although the problem was set up and we can show that, well, case by case, that the answer is unique, but it's hard to come up with general answers, and therefore it's hard to solve it in general. And also this method does not apply to ADS4 tensor 7 because this differential operator in that case actually is non-local. So we don't know how to interpret that in many space. And finally, there's a third method, which is basically a mailing version of the first one. So there's a nice trick to implement the word identities directly in mailing space. And the advantage of that is since we know all the Witten diagrams in any dimensions, now we can compute correlators in any dimensions. And that was actually how the first correlator in ADS4 tensor 7 was computed. But just as method 1, this is a case-by-case method, and it's difficult to get general answers. So before I go on, are there any questions about these bootstrap methods?
Could you please remind again what is D, curly D?
Curly D is just a differential operator, and it's completely determined by superconformal symmetry.
So it's sort of like a general solution of superconformal word identities can be presented like in this form?
Yes.
Or,
Right. Yeah. So this D is completely kinematic. Yes.
And it involves some kinematic dependence still, and that's why like the complete thing kind of has different analytic structure from H, right? This is what you're
right.
saying.
So in the n=4 story, this you have this partial non-randomization thing. So this is a free correlator, and this is like this is the product of something like 1 minus z times alpha and all the other variations. Yes.
Okay, thank you.
Any other
Can I ask something? Yeah, so, just general question. So what information from the bulk you actually need? Because it looks like you just bootstrap all these theories on the boundary, but some of the structures through Mellin space can naturally be represented as bulk exchanges and so on, but you don't have to give such interpretation. So I wonder if you actually borrow any information from the theories that are in the bulk. For example, in a routine of Frolov, they took the vertices, computed them, extracted result, and so on. But in your case, do you actually need any bulk whatsoever?
I don't need much information. So the only information I need is the bulk spectrum, but that can also just, I mean, that also follows just from repetitions. So these are the short multiplets. But I do need an assumption. The assumption is that in the exchange, the only operators that are exchanged are the supergravity states. So that's kind of the only input I need. So I'm not allowing myself to exchange like string states, for example. These are not these short multiplets. Does that answer your question?
So we can rephrase it as you borrow some information, mild information about spectrum from the bulk, but in a sense, everything well, the rest is just bootstrap on the safety side.
Exactly. So essentially I just need to input the spectrum of the supergravity. Then all the cubic and quartic vertices can just appear from that.
Yeah. Okay. Thank you.
Thanks for the question. Any other question?
Yes. So what is known about ADS3S3 case?
ADS3 tensor 3 actually has also been worked out. So there's a I haven't mentioned this. So there's something called a hidden conformal symmetry, which was first observed for ADS5 tensor 5. It turns out that is also present there. So using that, we have worked out like all the 4-point functions. But it's a slightly, so the reason I'm not discussing here because there's the kinematics is different. So their mailing is not a good way to deal with these correlators.
Okay.
Further questions? Okay, so if not, let me go on. So right, so in the previous slide, we saw that these bootstrap methods, they are powerful, but however, they are only successful in various limited domains, and they cannot provide us with a general picture. So for these 3 theories with maximal supersymmetry, only the ADS5 case was solved in general, and the other 2 cases we can get some partial answers, but we don't know how to solve it generally. And the bigger problem with this bootstrap approach is that this method prevents us from looking under the hood, in the sense that the bootstrap method only gives us the final answer, and we don't know why the answer should look like this. So if you want to understand the microscopic details of how holographic correlators are organized this way, then we need to use some other approach. And so that leads us to 2 of the goals of today's talk. So the first goal is to completely solve the other 2 cases, but now by using a more constructive method. And the second goal is to try to identify in these 3 cases, what is the common organizing principles for correlators from different theories. Right. Okay, so now to achieve these goals, we first need to figure out what is the thing we should look at. So the correct thing to look at is the full amplitude, not the reduced amplitude, which was very useful for ADS5 tensor 5. The reason is very simple. So first of all, the reduced amplitude, as I discussed earlier, we cannot really define for ADS4. And also it has very obscure analytic structures. We don't really know what it physically means. But by focusing on the full amplitude, we have some problems too, because the full amplitude is in general much, the size is much bigger than the reduced amplitude, and it's very complicated. So that led us to think maybe instead of trying to understand the full amplitude as a whole, maybe we can first try to find some simplifying limit, and we can first start by understanding that limit. And the flat space scatter amplitude gives us an idea for how to do that. So in flat space, we know helicity is very important because there's, for example, the maximal helicity violating amplitude is super simple. So that tells us we can do something to the helicities and to simplify the answer. Now we want to mimic this for the ADS case. But this thing we are going to do here is not exactly the same as in flat space because we are dealing with scalars. They don't have helicities. But we do have some polarization vectors that's associated with asymmetry. So that's why I'm going to introduce this limit, what we call maximally asymmetry violating. Basically, what we do is that we take the polarization vectors for operator 1 and operator 3, so these T1, T3, and we make them equal. And for the other 2 polarizations, we don't need to do anything. And now in terms of cross ratios, this means that sigma equals to 0 and tau equals to 1. And I'm going to define this MRV amplitude as a slice of this general mailing amplitude, where the cross ratios are set to these special values. So that is the definition of this limit. Now let's see how this limit really works in practice. So here I'm giving you the simplest 4-point function for ADS 7 times S4. So the external operators are the stress tensor multiplet. And you can see even this is the simplest amplitude, it is still a big mess because this the numerator here is this very long expression. However, if we go to the MRV limit I introduced in the previous slide, we find this very complicated expression now is simplified to this very nice one-line formula. And there are two interesting features I would like to point out. The first is that we find this MRV amplitude, it has singularities in both S and T, but does not have any poles in U. And the second feature is that it contains a factor of zeros. And these zeros, they associate with some double trace operators. Now let's try to understand why we have these features. And let's first start with the fact we don't have any singularities in U. So here I'm giving you a table. This table contains all the relevant fields that can appear in the exchange in the multiplet. So this multiplet is labeled by some integer p. This SP is the superconformal primary, and we have some vectors and also other scalars and also spin 2 particles. Notice each component field is associated with a Dinkin label, asymmetry repetition. Now we want to ask, how is this asymmetry information captured in the 4-point function? The answer is very simple. So this information is just captured by an asymmetry polynomial of sigma and tau. And these polynomials, you can think of them as the analog of conformal blocks, because they are the eigenfunctions of two-particle quadratic Casimir for the asymmetry group. So we have these asymmetry polynomials for each channel, for each permutation, and then we just need to check what happens in the MRV limit. And we find for the S and T channels, they are non-vanishing. However, for all the exchanges in the U channel, they become 0. So that explains why we don't have any singularities in U, because their asymmetry is suppressed. There's another way to say it. So when we take T1 equals to T3, that means in the U channel, the only representation we can exchange is the rank K1 plus K3 symmetric traceless repetition. And this repetition has overlap with the S and T channel repetitions, but it has 0 overlap with the allowed exchanges in the U channel. Are there any questions about why we don't have any U poles? Okay. Now let's move on to the second feature, which is this these zeros. So these zeros actually, they mean two things. So the first is that it means there are certain double trace long operators which have small twists. They get decoupled in this MRV configuration. And the location of the decoupled operators, so the conformal twist of the decoupled operators, they precisely correspond to the location of the zeros. So these are quite complicated statements. So let me try to unpack it a bit by using this simple example of 2-2-2-2 4-point function. So here we are seeing a table which gives the operator content in a long multiplet. It has different asymmetry repetitions. Now for all these repetitions to fit into the 4-point function, the long operator, the superconformal primary operator, has to be in the singlet repetition. Now so for each repetition, we can write down the asymmetry polynomial, and we can see what happens in the MRV limit. And we find all the first 5 repetitions, they just identically vanish. And there's only this 4,0 repetition that survives in this MRV limit. Now, so let me point out that the guy that survives is a superconformal descendant, and it has a conformal twist that is greater than the superconformal primary by 4. Now, on the other hand, we are dealing with large N series here. So all the long operators, they correspond to double trace and multi-trace. So the smallest twist we have for these long operators here is 4 plus 4, so, which is 8. But we see that in the MRV limit, this twist 8 operator is not going to show up, nor is twist 10. The first one we are going to see here is 8 plus 4, which is 12. And the missing numbers 8 and 10 precisely correspond to these zeros here. Now, to understand why they show up as zeros, we need to go back to the mailing repetition. So in the definition, we had, you remember we had this product of gamma functions. And here they're supplying us with some double poles. Now, these double poles can be problematic in the MRV limit, because if we perform the integral and we take the residuals, the double poles means we need to take one derivative, and the derivative can act on the cross ratios and it gives us some logarithmic singularity. These logarithmic singularities are associated with enormous dimensions, which are the hallmarks of long operators. But we argued just now that the long operators with twist 8 and 10, they should decouple. So the only way to resolve that conflict is that we need to introduce zeros, which soften these double poles so that they become only simple poles. Now, this phenomenon is completely general. It just follows from repetition theory. And more generally, we find that we should have 2 zeros in the MRV limit for U at these values. So are there any questions about why we have these zeros?
Why you don't have these zeros in other channels?
Because this limit I defined is not crossing symmetric. So, sorry. Yeah, so I pick 1 and 3, so that breaks the symmetry. You can also define this notion for other channels, but it's not necessary.
Okay, thank you.
Thanks for the question. Other questions? Okay. So, right, so we saw there's these zeros which follow from formal symmetry, but it turns out that these zeros are satisfied multiplied by multiplicating each channel. And that we can use as a non-trivial constraints to fix the contribution of all the component fields in the same multiplet. And eventually that will give us all the MRV amplitudes, as we'll shortly see in this slide. So let me explain how this is done. So first, we start with an onset for each multiplet. So this is just a linear combination of all the 6 fields. So here, these m's are the mailing amplitude associated with each written diagram. And these lambdas are some coefficients we are not fixing at the moment. Now, before we impose this condition of zeros, we first need to do something to the regular part of this mailing amplitude. So the reason has to do with the rigid behavior. So the rigid limit we are looking at here is the U-channel rigid limit, which means we take S to infinity and we keep U fixed. Now in this limit, we find the MRV amplitude goes like 1 over S. However, this behavior is not satisfied by a generic spin-L exchange diagram, because a generic spin-L exchange diagram goes like S to the L minus 1. But there's the simple way to fix that. Basically, is just to collect all the regular terms from this mailing amplitude and throw them away. And that gives us these improved exchange diagrams denoted as P here, which was called Polyakov rigid blocks in these papers. And that corresponds to just choosing a specific choice of contact terms. Okay, so now that we've improved this rigid behavior, now we can impose these conditions of zeros, and these zeros should show up at every pole. And it turns out this condition is strong enough. We can solve all these lambdas in terms of just the lambda for the superconformal primary. And this lambda s can also be easily determined because we already know all the superprimary 3-point functions. So following this, we now have solved all the MRV amplitudes, because all the MRV amplitudes can be written as the sum over MRV amplitudes of each multiplet. And by selection rules, actually, there are only finite many multiplets that are allowed. So in the previous slide, we solved the MRV amplitudes, but we can actually do much more. So we can actually start from this MRV limit, and we can obtain the full amplitude. And this can be done in 3 steps, which I will now explain. So the first step is to restore the sigma and tau dependence in the exchange contributions. So previously, we were setting sigma equals to 0 and tau equals to 1. But there's no difficulty in looking at general sigma and tau, because we just need to plug in these sigma and taus in these asymmetry polynomials. And then we use these exchange contributions in the ansatz, and that fixes all the polar part, the ones with simple poles. There could still be some extra regular terms. However, these regular terms, they cannot be arbitrary, because we can uniquely fix them by imposing the superconformal word identity in matrix space. Let me also point out that this division between what's singular and what is in the polar part and what's in the regular part, this is not unambiguous, because we can always move some terms from one side to the other. But the interesting thing is that we find that there's a very natural prescription to go from the MRV amplitude to the full amplitude, such that we don't need to add any further explicit contact terms. And the full amplitude is just written as exchange amplitudes. And this prescription actually has to do with the restoration of Bose symmetry. So let me try to explain what that means. So actually, in first step, when we restore sigma and tau, in this way, we find that we have messed up the Bose symmetry for this for the S channel exchange. So if we interchange 1 and 2 or 3 and 4, we find this guy does not go back to self. To fix that, we can track the problem down to here. So we find that at each pole, it has a factor of which is quadratic in -1 variables. That depends only on u, and there's no t, and that tells us why we don't have Bose symmetry. Now let me explain what these numbers here mean. So ij are the exponents of sigma and tau, p is the label of the exchange multiplet, and m labels the location of the pole. So we are looking at the pole at s equals to 2p plus 2m. So to restore Bose symmetry, we just need to get rid of m and put back in t. And we can do that because we have 2 conditions. The first one is the pole we are looking at, and the second is, which follows from definition, it's plus t plus u equals to the sum of external dimensions. And we can trade m for t. Once we do that, we find the Bose symmetry is restored, and we still have all the good behavior in the MRV limit. We can do similar things for the T channel and U channel, but they are just related to the S channel by crossing. So that was some very lengthy technical steps, but the upshot is that we now find that the full 4-point amplitude can be written as a sum over these exchange contributions from multiplets labeled by P. And this P is restricted to a finite range as follows. And this restriction comes from 2 things. The first is that asymmetry impose selection rules, and the second is that extremal couplings should vanish. And the important thing here is that if we follow this prescription, we only need these exchange contributions. We don't have any additional contact terms. Are there any questions? Okay. So, right. So this construction was for ADS 7 times S4, but it's completely similar for the other two cases. Essentially, it follows from the fact that the multiplets, they look basically the same. Now, let me summarize. So we started from defining a limit where things are much simpler and easy to construct. And then after solving this limit, we use symmetry to get the full amplitude. And the amplitudes, they have the following structure, and they can be written as sum of exchanges with no contact interaction. And it can be written as a sum over simple poles. These residuals at each pole can be explicitly computed using the procedure I outlined earlier. And here's the final result. So the residuals, they can be broken into three parts. There's the part with which is a polynomial in the minus variables, it's quadratic, and then there are some factors of gamma functions. So note here, I wrote everything in terms of this parameter epsilon, which takes three physical values, and correspond to the three maximally supersymmetric backgrounds. And the fact that we can write everything down in terms of a single formula means there is some universality for these amplitudes from different theories. Now, let's not stare at this answer because it's quite complicated. In the next slide, I'm going to show you there's actually some very interesting structure which allows us to write it in a more compact way. So it turns out that these amplitudes can be massaged in such a way that we can see the natural appearance of a lower dimensional spacetime. And this emergent dimensional reduction actually is closely related to the Parisi-Sourlas supersymmetry that was first found in the STEMMAC context. So let me very quickly outline how this can be seen. So first, let's focus on the ADS part, which means we only care about the minus variables. Let's first get rid of this factor k here. To do that, we noted that it's a polynomial in CNU, so we can just.
Can I ask a question? Yeah.
Yes, please.
So this superconformal symmetry doesn't really play, high dimensional conformal symmetry doesn't play any role in this, right? Because it appears in ADS 5S5 case, but not in other cases.
Right. This hidden conformal symmetry is not there for the other two cases.
Okay, so it has nothing to do with this dimensional reduction or anything like that, right? So that's
right. Also, it hasn't anything to do with that. Yes.
Yeah. Okay.
Other questions? Okay. Right. So I was saying that we can peel off this factor. We are basically just using the simple property that y dy acting on the many transformation brings down the exponent. Okay. Now the other minus the variables that's remaining is just a sum over posting s. Okay. Now it turns out that this thing can be actually written precisely as the sum of only scalar exchange diagrams, but still in the same ADS space. There are only three of them. And these exchange diagrams, they have some shifted dimensions. So we have the following form. We have a differential operator acting on a linear combination of scalar diagrams. So this is quite similar to this weight shifting operators people sometimes discuss. Now, there's the further surprise there. So this linear combination of three diagrams, if we look at it closely, we find that it secretly is just one scalar exchange diagram, but now in a dimensionally reduced spacetime. So the ADS space has now 4 dimensions less. So this identity seems quite bizarre, and we want to understand why we have this identity. And also I mentioned the Parisi-Sourlas earlier, so let me now try to explain what these things have to do with each other. So here, let me very schematically remind you what is Parisi-Sourlas supersymmetry. So a very long time ago, people were looking at random field models in d dimensions, and they realized that the calculations in the d-dimensional theory coincide with another model, but without disorder in 2 dimensions lower. And to explain this coincidence, Parisi and Sourlas, they came up with this observation. They found that the stochastic equations, they actually have a supersymmetry. And this supersymmetry can be realized by introducing 2 fermionic directions. And this superspace has this OSPD/2 symmetry. At fixed point, this supersymmetry can further be enhanced. Now, here, this supersymmetry actually is quite unusual from the high-energy theory theorist perspective, because the supercharges, they don't obey statistics. So it's not unitary. But anyway, so the main lesson from this is that in path integral, these fermionic directions effectively eat away to bosonic directions, and therefore reducing the space dimension. So this is a very old story, but it was recently revisited by from the conformal bootstrap perspective by Slava and friends. They derived many interesting kinematic results, and among these results is a very beautiful formula for relating conformal blocks in different dimensions. So on the left-hand side, there is a single conformal block in d-2 dimensions, and on the right-hand side, it's a linear combination of 5 conformal blocks in d dimensions, and these c's are just numerical coefficients. We can also view this combination on the right-hand side as a superconformal block under this superconformal Parisi-Sourlas supersymmetry. Now, this relation actually can also be lifted into ADS. And there's a similar dimensional reduction formula for exchange-Witten diagrams. So it was pointed out in this paper here. And the prescription is very simple. We basically just replace every conformal block with the corresponding exchange-Witten diagram. But let me also point out this is not a trivial generalization of this relation, because we can decompose both sides into conformal blocks. This relation guarantees that all the single trace conformal blocks are matched on both sides, but there are also infinitely many double trace conformal blocks which need to non-trivially conspire in order to cancel. So that's the general case, but we only need the simple case where L equals to 0. For L equals to 0, this further simplifies into just 2 terms. So we have a scalar diagram on the left, and we have 2 more scalar diagrams on the right, but it has dimension shifted. Now, in the previous step, we go from d to d-2. We can also use it again to go from d-4. And when we combine these 2 formulas, we find that this combination we saw earlier is precisely a single exchange-Witten diagram in 4 dimensions lower. So that was the connection with Parisi-Sourlas supersymmetry. Now, there's also a completely analogous reduction for the asymmetry part. And we see that the internal sphere, which was originally SQ, now becomes SQ minus 4. So that's how we can see that there's the emergence of a new spacetime where both the ADS part and the sphere gets reduced by 4 dimensions. Right. Now, this observation also gives us a very compact way to rewrite our results. So now the exchange amplitude can just be written as a differential operator K, which follows from the factor K and acting on a single exchange diagram. This exchange diagram is just a scalar diagram in 4 dimensions lower. And also it's multiplied by an asymmetry polynomial that's related to this dimensionally reduced sphere. And this way to write the result is also quite suggestive. So it seems to suggest that there's a formally lower dimensional C theory that involves only scalars. The C theory has the same spectrum as the superconformed primaries, and also the same cubic interactions. And from the C theory, we can easily compute all the 4-point functions, and we can recover the correlators in the full theory by basically just addressing these seed correlators with some differential operators. Yeah, let me now very quickly switch gear and discuss another thing we looked in the recent paper. So in these holographic correlators, there is a wealth of theory data, and we can try to extract this data. But here, let me just focus on some protected information, which is encoded in the so-called twisted correlator. So recall we had this superconformal word identity. And it's easy to check that if we set the asymmetry cross ratios in these special ways, which is known as a twist, then the twisted 4-point function will become either meromorphic or topological. So this phenomena actually can be systematically explained in terms of superconformal twisting. It's called a color algebra in 40 and 60, and topological quantum mechanics in 3D. And this construction caps out a protected sector of this series. I'm not going to explain in detail how this works, but let me just very schematically say that this construction is to just restrict certain protected operators either on a plane or a line, and choose special asymmetry positions determined by their locations. And then for such operator configuration, one can define a nilpotent supercharge Q. With respect to this supercharge, the twisted operators are close but not exact. And also the twisted translations are Q exact, and therefore making the twisted correlators holomorphic or topological. Now, this is a very strong statement about what happens to these holographic correlators. And actually, we can also explicitly check that from our supergravity results. So basically, what we do is just to take the residuals and perform the twisting. And we saw that the cancellation of the non-monomorphic piece actually requires contributions from all 3 channels. And they need to cancel in a very precise way. And it gives a non-trivial consistency check for our results. And moreover, not only can we check the twisted correlator is meromorphic, we can also check it matches with, the twisted correlator is also the correct one. So we can also perform the calculation independently in the field theory based on the following simple facts. So the meromorphic function is just determined by its singularities, which are controlled by singular OPEs. And these singular OPEs we already know. And so using this, we can compute these meromorphic correlators, and we find in these 2 cases, in these 2 approaches, they precisely agree. The 3D case is slightly more difficult technically. So instead of checking their topological, we just extracted some 3-point coefficients for this protected sector, which in principle can be compared with future localization computations. So I'm out of time, so let me now wrap it up. So in today's talk, I presented a constructed derivation for these 3-level correlators in all theories with maximal superconformal symmetry. The crucial observation is there's the simplifying limit, which is required by superconformal symmetry. In this limit, the amplitudes, they have many interesting features. They don't contain poles in a certain channels. They have also a factor of zeros, as well as improved rigid behavior. And these simplifying features allow them to be easily computed. Now, studying this limit also tells us how to get the full correlation function. The full correlation function basically is just obtained from this limit by using symmetries. There's one nice feature I think I should emphasize, which is the milling amplitude can be naturally written in terms of just exchange amplitudes with no additional contact terms. So this feature implies there is certain on-shell constructibility. Now, this absence of contact interactions actually was also observed at the level of 5-point functions for ADS5 and SIS5. And another thing is that we saw these results. They can be massaged, in a way, and we naturally see there's a lower dimensional spacetime showing up. And this structure allows us to compactly write the amplitudes in terms of only scalar amplitudes from lower dimensions. There are many things we can do in the future. The first is to extract CFD data and also go to higher genus. So there's a lot of data containing these holographic correlators. We only looked at the protected sector, but there are also unprotected data which can be further compared with localization as well as numerical bootstrap. Also, in the theory, for these three theories, we have now obtained all the tree level correlators. That's basically everything we need to extract the data and then go to one loop using this ADS unitarity method. So such research has been quite advanced for the ADS5 case, but it has not, it's only starting for the other two backgrounds. We can also extend this MRV approach to both higher point correlation functions and also theories with less supersymmetry. This is currently underway, and we actually saw many interesting new phenomena. There's also a very interesting question about this Parisi-Sourlas type dimensional reduction. We may want to know whether this is just a coincidence for a 4-point function, or it is a general property for arbitrary n-point functions. So if the latter scenario is actually correct, then we will have a very efficient way to compute n-point functions. Also, there are many things we can do by trying to find more analogies with flat space scattering amplitudes. So we can just take some ideas and structures which we already know in flat space and use that as an expression to find something similar in ADS. So in today's talk, there's a rough analogy between this MRV and this MHV notion. As I mentioned in the previous slide, there was this observation of no intrinsic contact terms. So that makes it hopeful that maybe we can also find some holographic version of BCFW recursion relations. And of course, there are many other interesting things to look at. So recently, there's been some work about finding an ADS version of color kinematic duality, as well as trying to find a CHY-like formalism by using MB2 strings. But there are also many other things we can try to do. So, so I will stop here. Thank you very much, and sorry about going over time.
Thank you for a nice talk. Are there any questions?
Can you please comment maybe once again on the absence of contact terms? How does it happen?
It's an observation. We don't, right. Sorry, yes. So here we just found it by using this prescription to go from MRV to the full amplitude. So it was the requirement for restoring this Bose symmetry, and this prescription just absorbs some contact terms, and we find there's no additional contact terms in addition to that. Now, in principle, that doesn't need to be the case, because there could be some terms that are linear in the minus variables. So these are the two direct interactions which cannot be absorbed into these exchange amplitudes in this way. Then we don't have this we no longer have this property. But that didn't happen. We don't understand why it didn't happen. Sorry, let me make another comment. Well, in a way, we understand this. So if we require that we have this Parisi-Sourlas supersymmetry, then we wouldn't have these extra contact terms because they would break this symmetry. But that's a strong statement to make because we don't know where this Parisi-Sourlas supersymmetry come from.
And just this separately, contact terms separately, they don't satisfy both the symmetry, or why you don't have them?
We can write down contact terms which satisfy both symmetry. Mm-hmm. It's just that they don't show up here.
And how do you know that?
Oh, because the contact terms can be checked by, we can include some extra contact terms and see if four answers satisfy the superconformal word identity embedding space. Mm-hmm. And we checked that in all cases, like 10, 20 different cases, that these extra contact terms, they just vanish.
Mm-hmm. But is it similar? Well, if I remember the story correctly, but in the original computation by Residuals, there were some cancellations, also some two derivative terms, if I remember, maybe I forgot and everything, but some two derivative terms in quartic vertices, they disappeared magically if you use equations of motion or something like this. Can you comment on that? Maybe that's related, but sorry if I misinterpreted it.
I think in Gleb and Sergey's story, the cancellation was for the Fodor terms, right? Is that right, Gleb?
Yeah. So originally you get terms with up to 6 derivatives. 6 derivative terms you can cancel sort of easily, but then there are 4 derivative terms, which is a pain, but you still can cancel them by integrating by parts using various identities for spherical harmonics. So at the end you end up with the action which contains only second derivatives. So this action is of sigma model type, which is kind of natural because you start originally from sigma model in 10 dimensions. So you expect that at the end, after the reduction, it's better to get again the action which contains only 2 derivatives. And high derivatives appears because when you perform this reduction, you need to solve a number of constraints because you have symmetries around ADS5 crosses 5 background. So you have constraints. When you solve them, then this high derivative appear, but then you sort of see that at the end they somehow magically cancel out. I'm not sure that it's related to exactly to what you say now in your story about this magic cancellation. But maybe in respect to that, I can ask you the following. First question is, for this case, ADS4 crosses 7, you have now new results.
Yes.
And do you know how these correlation functions look like in X space? Is it something nice or special? I know that in principle, you can follow the same procedure of computing correlation functions as you do in other dimensions, but then you get D functions with half integer index and actually you get an infinite sum of them. So it's not clear at the end how to sum them up. Exactly. But it seems like with the methods which you develop now, you can maybe look at how they appear in the X space when you do inverse Milling transform. I'm not sure if you know the answer, but if you know, please.
Yeah, that's the excellent question. So we tried a little bit for this simplest case 2222. So indeed, as you say, that these diagrams, these results, they require infinitely many D functions in order to be written down in position space. But here we can use this Parisi-Sourlas structure now just to reduce it to scalar exchange diagrams. Mm-hmm. But still, in the scalar exchange diagram, there you still need to have these D functions with half integers. So we don't know how to write it more compactly. Maybe we need to introduce other functions. Mm-hmm.
maybe the other question. So do you think now with this new techniques, when you know these amplitudes and you know that eventually everything is reduced to one scalar exchange, right? Is it possible now to look back and write down sort of an effective action, a new effective action, not the one which we computed, but a new one, totally new one, from which you can sort of get this result at once?
Yes, that's an excellent question, and that's So the answer is we don't know so far. So there's only one 5-point function we computed for ADS 5 times 5. So maybe we can try to see if this answer can also be massaged in such a way that we also have this Parisi-Sourlas supersymmetry. Then, if that's the case, then indeed what you say is very promising. We can just write down effective action just for the scalars. And then in this scalar theory, we compute the seed correlators, and then we dress them up with some differential operators, which are in a sense just determined by superconformal symmetry, and then we can get the full answer.
I think it would be useful if you then think about extending these to loops. It would be good to have this very compact action for 3-level amplitudes,
right?
And you can think how to
yes,
make high loops out of it.
Yes.
And also ADS 4 cross S7 is of course a special case because the conformal field theory is 3-dimensional. 3-dimensional conformal field theories are usually rather strange.
Right.
I think there is no Zamolodchikov C theorem for this case. So I'm not sure that it's related to the fact that you have this infinite number of poles appearing without truncation, which you have in the other case, but yeah, something special, very special happens here, definitely.
Yes, but from our perspective, it seems okay. Actually, we can also do things like ADS6, like what product of ADS6 times hemisphere 4. So there you also don't have a truncation of poles, but also superconformal symmetry fix everything.
Okay. Yeah, thank you.
Thanks.
Could you remind us what was the motivation for this introduction of Parisi-Sourlas symmetry in Ryczkow et al. Paper? Why they used? What was the connection to conformal blocks?
Right. So they were trying to, so in the Parisi-Sourlas literature, so this dimension reduction, for example, does not happen for 3D Ising, because the reduced series, random field Ising 3D gets reduced to 1D. It has different phase structures. So they were trying to figure out why this Parisi-Sourlas supersymmetry works when it doesn't. So they were trying to approach it from a more non-perturbative perspective, which is from the conformal bootstrap. So they would that's the motivation for them to find the realization of that in terms of conformal blocks and so on. And for me, it was not really related. I just I find this result interesting. I was trying to just generalize this into ADS to see if it can be also realized. So this was from last May, but later we find that this structure also makes an appearance in these 4-point functions of maximally superconformal series. So yeah, it's a surprise. We don't know why these two things are related.
But that's specific to superconformal, to maximally superconformal, right?
Actually, not really. So we are now working on theories with less supersymmetry, and that structure also persists. So instead of going down by 4 dimensions, we find now they go down by 2 dimensions.
Interesting, because originally, yeah, this Parisi-Sourlas have nothing to do with supersymmetry and
right,
yeah, and conformal symmetry, because it's just kind of
that's right,
averaging.
And is this true for any delta or for some specific values of delta?
This is true for any delta.
Okay, I wanted to ask another thing. So there was recently a paper, maybe you saw it, Heslop and colleagues. So
Yes.
they computed, well, similar things, I think for radius 5 cross S5 by, well, essentially doing some kind of 10-dimensional computation immediately.
Mm-hmm.
Can you do something like that here as well? Like
Here, yeah, that's an excellent question. We haven't thought about it. It could be that we can also consider some. It can be just written in terms of 3 exchange diagrams coming from TND. I think it's very interesting, but we haven't tried to do that.
Thank you. Any more questions? Okay, then thank you very much for a nice talk.
Thank you for having me.
Thank you.
And see you next time to everyone.
Thank you.
Right.